quantum physics has always been a realm filled with mystery and wonder, home to phenomena that defy our intuition. One such phenomenon is superradiance, a synchronized burst of light emitted by atoms, which is both fascinating and elusive. While superradiance has been observed in confined optical cavities, its occurrence in free space has remained an unsolved problem. Recent breakthroughs, however, bring us closer to understanding how atoms might synchronize in the vast expanse of free space. This discovery is not just a leap in scientific curiosity. It's a step toward revolutionizing how we interact with the quantum world. In this video, we'll dive into the science behind superradiance, explore the latest research breakthroughs, and uncover why this discovery is so crucial for the future of quantum physics and technology. What is superradiance? At its core, superradiance is about synchronization. When atoms interact with photons in confined spaces, like optical cavities, they emit light in perfect unison, producing a burst of energy far more intense than if each atom acted alone. This phenomenon occurs because the mirrored walls of the cavity allow photons to bounce back and forth, creating a feedback loop. Atoms absorb these photons and re-emit them, aligning their emissions to create a collective amplified output. In contrast, the dynamics change drastically in free space. Without the reflective boundaries of a cavity, photons disperse in all directions, and each atom emits light independently. This lack of synchronization results in a disorganized emission pattern, making superradiance seem impossible in such an uncontrolled environment. In a cavity system, the interaction between atoms and photons is all-to-all, meaning every atom can influence the emission of every other atom. This interconnectedness is key to their synchronized behavior. In free space, however, these interactions are limited and scattered, similar to trying to have a conversation in a noisy, crowded room. The absence of feedback and alignment makes it difficult for atoms to collectively emit light. Achieving superradiance in free space isn't just a technical hurdle. It's a fundamental question in physics. Can we create conditions under which independent atoms behave collectively without boundaries? A breakthrough experiment. A recent experiment captured the attention of the scientific community by attempting to observe superradiance in free space. Researchers used a pencil-shaped cloud of ultra-cold atoms arranged in free space and excited them with a continuous laser. Their goal was to determine if these atoms could synchronize their emissions, potentially hinting at the elusive phenomenon of free space superradiance. The initial results were intriguing. Researchers observed signs of partial synchronization, where some atoms aligned their emissions. This raised the possibility that superradiance could occur in free space, challenging decades of assumptions. However, the data sparked debate. Was this truly superradiance, or merely a coincidental alignment under specific conditions? Theoretical insights. To probe deeper, theoretical physicists at the Quantum Physics Division and the National Institute of Standards and Technology (NIST) conducted advanced simulations. In these simulations, each atom was modeled as a dipole capable of absorbing and emitting photons. These simulations replicated the experimental conditions and provided insight into the observed behavior. The findings revealed that the observed partial synchronization wasn't true superradiance. Instead, it was the result of specific experimental conditions, such as the density of the atomic cloud and the laser's intensity. As Anna Maria Ray, a leading theoretical physicist at GILA, explained, the interactions in free space can be weak enough that simplified treatments are possible. However, it wasn't initially clear if that would hold true in this experiment. The number of accessible states in free space increases exponentially compared to a cavity system, making the problem far more complex. Graduate student Sana Agarwal, the paper's first author, elaborated on their methods. We considered a microscopic model in which every atom acts like a dipole and used it to study the emergent properties of the entire atomic cloud. The laser beam is a plane wave, imprinting a specific phase pattern on the atoms, which is crucial in determining how the atoms interact. The researchers simulated various conditions, including different laser powers and atom densities, to see how these factors influenced the system's behavior. Their simulations showed that a mean field approximation, which simplifies the complexity by treating the atoms as classical magnets, was sufficient to explain the results. The road ahead. While the findings suggest that true superradiance in free space may not have been achieved in this experiment, they open new avenues for exploration. The quest to understand how atoms might synchronize in free space is far from over, and this research represents a significant step forward in our understanding of quantum phenomena. As we continue to push the boundaries of quantum physics, breakthroughs like these bring us closer to unlocking the secrets of the quantum world, and to revolutionizing technology in ways we've only begun to imagine. Ray noted that their simulations successfully reproduced the experimental observations in the dilute regime. However, she emphasized that exploring new regimes where current theoretical models become obsolete will be particularly exciting, as it will necessitate more advanced treatments. This collaboration between experimentalists and theorists exemplifies the essence of scientific inquiry, where hands-on experiments and rigorous simulations work together to bridge the gap between observation and theory, offering deeper insights into the behavior of atomic systems in free space. This research builds upon foundational quantum theories, such as the Dicke model, which first described collective atomic behavior. By challenging and refining these theories, the study pushes the boundaries of our understanding of light-matter interactions. Additionally, parallels can be drawn with Bose-Einstein condensates, where particles synchronize at extremely low temperatures. Such connections open up new avenues for exploring collective quantum behaviors in diverse contexts. Another key theoretical framework relevant to this work is spontaneous symmetry breaking in quantum systems, a principle often observed in condensed matter physics. This concept explains how systems transition from a disordered state to a more ordered one. In the context of superradiance, spontaneous symmetry breaking could provide insights into how partial synchronization emerges and under what conditions a full transition to superradiance might occur in free space. This idea complements the Dicke model by offering an additional layer of explanation for the observed phenomena. One of the most exciting aspects of this research is its potential to inspire new experimental designs. Increasing the density of atomic clouds or modifying their geometry could create more favorable conditions for synchronization. Advanced optical techniques might also enable greater control over photon directions, unlocking new possibilities for achieving superradiance in free space. Theoretical challenges remain just as compelling. While current models work well for dilute systems, they struggle to accurately describe dense, highly interactive atomic arrangements. Developing quantum-level simulations that capture these complexities is a crucial next step. Such models could improve predictions of free space system behavior and guide the design of future experiments aimed at achieving synchronization. Ultimately, this research highlights a fundamental truth about science. Progress often arises from bold questions and uncharted exploration. The pursuit of understanding superradiance in free space is a testament to the power of curiosity and collaboration, challenging us to rethink assumptions and push the frontiers of quantum physics. Thank you for watching. Stay tuned as we continue unraveling the mysteries of the universe, one quantum leap at a time.